Water Potential by Alexis Perdue and Natalie Conrad. The goal of our project is to know how to calculate water moving in and out of the cell. This is the water potential formula. It has two major components, pressure potential and solute potential. Both of these are used to determine water potential. This is water potential. Its symbol is known as PSI. This lets us know if water goes in or out of the cell. This is pressure potential. It measures the amount of pressure within a cell. This is solute potential. This measures the amount of solute within the cell. This is the solute potential formula. This is in the water potential formula to help us calculate the actual water potential. Solute potential can be broken down into a couple components, so let's go over them. I is the ionization constant. We will show you how to calculate this in a second. Next is C, which is the concentration. It is always given to you in moles in the problem. Next is R, which is the pressure constant. This number remains constant throughout the problem. The number you use is 0.0831. Last is T, which is temperature. You have to have the temperature in kelvins, and we will show you how to convert degrees Celsius into Kelvin in a second. When determining what I is, you must look at the solution to see how many ions it breaks down to. For example, sucrose is a sugar. Since it's a sugar, its ionization constant will always be 1. Anything that ends in ose will always be a sugar that equals 1. Next is NaCl. This breaks down into 1 Na and 1 Cl. You add these together to get your ionization constant equaling 2. Last is H2O. So again, the H has 2 and the O has 1. Therefore, the ionization constant would equal 3. Okay, so calculating Kelvin is very easy. All you have to do is take the degrees Celsius the problem gives you and add 273. This gives you the temperature in kelvins. Now, one key note to remember is that water moves from areas of high to low concentration. This lets us know if water is going in or out of the cell. Okay, so now that you know how water moves, let's practice. So remember, water goes from high to low concentration. So in beaker 1, to the left, 9.84 is higher than -6. So water is going to move into the cell. Looking at the beaker to the right, 2.5 is higher than 0.3. Therefore, water will move out of the cell. Okay, now let's look at some key vocab to remember. Isotonic is when you have equal osmotic pressure and the same water potential. Hypertonic is when you have a higher osmotic pressure than a particular fluid. Last is hypotonic. This is when your osmotic pressure is lower than a particular fluid. Problem 1. The value for water potential in root tissue was found to be -2.6 bars. You take the root tissue and place it into 0.2 molars of NaCl at 23 degrees Celsius in an open beaker. What is the water potential of the solution? Okay, so first you need to figure out the solute potential. Here's the formula. Let's break it down. So first, your I is going to be -2 because NaCl ionizes into 2 ions. Your C is what's given to you in the problem, 0.2 moles. Next is R, which is always 0.831. Last is temperature, so take 23 and add 273. That equals 296 degrees in kelvins. Multiply all these together and you get -9.84 bars. Okay, so now that you have your solute potential, let's find the water potential. So you take -9.84 and add 0. The pressure potential is 0 because the container is open. So now you add your water potential and you get -9.84. Okay, so with the cell equaling -2.6 and the outside being -9.84, the water moves from areas of high to low concentration. So water will leave the cell. Problem 2. The value for water potential in a cell was found to be -10.24 bars. You take 0.4 molars of solution of sucrose at 19 degrees Celsius in an open beaker. What is the water potential of the solution? Okay, so same thing. Let's calculate solute potential. I is going to be -1. The concentration is going to be 0.4. The rate is going to be 0.0831, and the temperature is going to be 292. You get -9.71 bars. After you multiply, add -9.71 plus 0. The beaker is open, and now your water potential is -9.71. Looking at the cell, it's -10.24 outside the solution, and it's -9.71. Water moves from areas of high to low concentration, so water is going to move into the cell. Hypotonic solution, plant cell versus animal cell. When both of the cells are placed into the solution, they both take in H2O. Animal cells continue to take in water until their cell bursts open. Plant cells take in water, but don't burst because their cell wall doesn't allow too much water to enter. Thank you. Please subscribe below.